So in this video, we will look at electrical generators and how they operate. I put here electrical generators. And they all have more or less the same idea. If you take a magnetic field, so you set up some magnetic field, say it points to the right. And typically the magnetic field is a constant value. Here's the magnetic field B, points to the right. And this magnetic field could be set up by some permanent magnets, the North Pole here and the South Pole here, or it could be set up by electromagnets. So maybe there's some kind of so let me draw another option. So you could have a magnetic field that points in this direction, and this could be set up by an electromagnet, so that perhaps here you would have a solenoid. Right? You have a solenoid, and then this solenoid ends like so, and it produces a magnetic field that points out that way. So this magnetic field that points this way, and maybe on this side, I should have drawn it bigger. Or what I could do is do this and then just get rid of the bottom few lines of the magnetic field. So maybe I'll take this one out, and now this looks a little more legitimate. So what I have here is the magnetic field that points out of this out of this loop and into this loop and out of this loop and away. And so what I would have is magnetic field all the way around like that. But the point is that the magnetic field between the two coils would just point to the right. So I would also have magnetic field here. The same thing actually would happen you'd have the same thing on the left hand side. That is, if you have a north and a south pole, and if there's a south pole here, that means that somewhere else there's a north pole, and so you'd have these magnetic field lines looping around. But anyways, let's get rid of all of that. So this thing here goes away. We set up a magnetic field that is steady, that is constant, points to the right. And then we're going to take a loop, and we're going to put a loop in this magnetic field. But I'm going to do it a little differently. So what I'll do is here's a single loop, and it has vector A, area A that points like this, vector A, and it is perpendicular to the surface. And I'm going to add something else to the picture. I'm going to put here a coil. That we have a coil. Right, there's a solenoid. A solenoid here with a certain number of loops. There's a number of loops n. And vector A. We're going to add vector A to this. Area vector, it is perpendicular to the surface. And so now let's see how we do this. What we want to do is we want to generate a current in the loop. And the way we will do it is, let me select this. And then we're going to put this loop in a magnetic field. Now there's a flux through this loop. But constant flux doesn't help us. What we want is a variable flux, is a changing flux is what we want. And so as I move this loop, let me set this up so that it rotates this way. Okay. So now I'm going to rotate this loop, and as I rotate this loop, the flux through the loop is changing. And if the flux is changing, then there is a voltage in the loop, or EMF in the loop. And that implies that there's a force on the charges, and the charges have to flow, and so there's a current. So if I can rotate this loop through the magnetic field, then there will be a current in the loop. You can also think of it this way. If the loop rotates through the field, then that means that charges within the loop also move through the magnetic field, and charges moving through the magnetic field experience a force, and so they will have to move. So a rotating loop will have charges that move. How exactly do they move? That's yet to be determined, but if I can rotate a loop like this, then I'm going to have a current that flows in this loop. This actually will give me an AC current. Let's take this out, and let's state that somewhere here on the side. Select this. So a rotating loop was going to give rise to an alternating current, AC. You will not be getting DC out of it, at least not in the way I drew it here. You can modify that AC to be a DC, but as it stands, it will always be an AC in this way. Now let's take a whole loop like this. Let's take a whole solenoid like this, and let's bring that into the magnetic field. So we're going to place a solenoid here, and this is actually a proper picture for a generator. All of the generators, virtually all of the electrical generators, will look like this, where instead of having a single loop, you will have a whole bunch of loops. You will have a solenoid, and you want that because the more loops you have, the more of a voltage you can generate. If you remember from the equation, let me state the equation. Perhaps I'll state the equation. That would be a good idea, I think. The equation for voltage, for EMF, is that EMF, which is voltage, maybe a different color. Let's go with this. So EMF, or the voltage, is minus n number of loops times the changing flux, magnetic flux. Okay, this is the Faradays law. So if I want to generate a voltage in a loop, then what I need is changing flux. But if I want to generate a lot of voltage, then I want to make sure that I have a lot of loops. And so now what I'm going to do is I'm going to take this here, and I'm going to put it in the magnetic field. That's in the magnetic field. There's a flux through this solenoid. But the flux is steady, the flux is constant, it's not changing, so there is no current yet. However, as soon as I start rotating this thing, the flux through the loop changes, and the changing flux will generate a voltage in the loop, and so the charges will flow. And it turns out that the more of the loops I have, the bigger the voltage, but also the faster this thing rotates. The more of a the more the magnetic flux changes, and therefore the bigger the voltage as well. So if I wanted to have a high voltage, right, so I think I'm going to leave this, maybe I'll set it up like this at an angle. Let's maybe move it down here. So, oh, that's right, I gotta set this up. So if I want to have a high voltage, if I'm looking for a very high voltage, so if I want high delta V or EMF, then what I need is, well, I need a big number of loops. I need n to be large. The bigger n here, the bigger the voltage or EMF set up in the loop. And I want to minimize time, the delta t, in which the flux tends to change. And so what that means is that for my specific purpose, for my specific picture here, I want this thing to rotate. I want this thing to rotate fast. If it rotates fast, then the change of the flux is rapid. It is large, and large change of a flux indicates a large voltage. And so this is the idea behind the generator. Every generator works like this. What I'm gonna add to it though is a picture that looks perhaps a little more perhaps a little better. So here's a picture of a generator. Right, and so what you have here is, well, you have the magnet with a north pole and a south pole, and therefore the magnetic field points from north to south. And then you have a hand crank here, and this crank here rotates the loop that is within the magnetic field. And then that loop, if it rotates through the magnetic field, then there's a changing flux through the loop, and therefore there's going to be a current in a loop, and that current then can flow. You can follow the path of the current. It goes like this, clockwise, goes like this, comes out this way, goes into the bulb, comes out of the bulb, but then flows back into the loop. Now the hand can be replaced with many different things. So you could, let's maybe draw it like this here. You could have a north pole and a south pole, and then you have a magnetic field that points this way, the magnetic field B. Then you have some kind of a loop here, and then this loop can be rotated by by something. And so maybe I'll draw something to the effect of something like this here. And then from this loop, you will have some sort of a connection that comes out and then goes through some resistor R, and then this thing comes back into the loop here. That's basically it. But then the question is, what is it exactly? What can you use to rotate this little piece here? Well, you could use the wind, so you could attach some kind of a propeller here that the wind can rotate this thing. So as long as you can make this thing rotate, you're all set. And you could use the wind, you could use the water, you could use your hand, you could use your feet, you could use what else could you use? You could use a bicycle if you wanted to. You could attach a bicycle wheel to this thing and rotate the loop in a magnetic field and end up with a current. All right, so the equation is here for the EMF set up in this generator, but we should derive it. Let's derive it. So I'm going to go back to the previous picture. All right, so this is what we have. Let's start with the let's actually clean up some of these things. So I don't think I need this here anymore. AC is going to come back to us, but well, that's going to come back to us. So what I have is I have the equation for the EMF, and I also have the equation for the magnetic flux, and that's B times A times the cosine of the angle theta. Now the magnetic field is constant, area is constant. The only thing that is changing is this angle theta, which is the angle between A. Theta is the angle between the vectors A and B. But the point is that the magnitude of B doesn't change, the magnitude of A doesn't change, it's the angle between the two that changes. So let me take this equation, this EMF, and rewrite it a little differently. If you're in 1202 class, if you did take calculus, this should make sense, and if you didn't, you can skip the next minute or so. But you could rewrite this as minus N times d of the flux dt. So d stands for the delta, and that there's your derivative here. And this amounts to minus N times d dt of BA cosine of the angle theta. Now B and A are constant, so you can pull them out, and you have minus N BA times the derivative with respect to time of cosine of the angle theta. Now theta is not a constant, so you can't just pull this out, but you have to express theta in terms of time, t. That's fairly easy to do. See, theta is just the angle through which this thing rotates. So I'm going to write here that theta, this is the angular displacement. And this could be in radians. In fact, we would want this in radians here. Omega is a speed at which this thing rotates. And so omega is delta theta over delta t. But we will simplify our life and we will just say that this is theta over t. Further, in the we're going to make a simplifying assumption that the omega is constant. So omega is constant. In other words, this thing here rotates at some omega, which is constant. You know, maybe 5 revolutions per second, or maybe 20 revolutions per second, whatever it is. It moves at it rotates at a constant rate, constant speed here. So I can write this from here, from this little expression here, I can write that theta equals omega times t. And so now I can go back to this equation here and write that this is minus n b a times d dt of cosine omega t. Now I can easily take the derivative of this expression. So EMF for the generator in my picture above would look like minus n ba times the derivative of cosine is just minus sine, so this would be minus sine of omega t, and then times omega. I still have to take the derivative of the expression on the inside times omega. And so what I have is, well, that's basically it. EMF as a function of time. So the voltage in this loop is going to vary with time in the following way. It's going to be n times b times a, all of this is constant, times the sine of omega t. And omega, of course, it is the angular speed or angular frequency. It's the same thing. And that would be 2 pi times f. So the expression for the EMF in this generator that I gave you, and in virtually all of the generators, is this equation here where omega is 2 pi f. So let's maybe move this up. Let's see if we could draw a picture here. What we get for the voltage then, because this is of course just the voltage, what we get for the voltage is that we start at 0 because it's a sine, and then this thing goes back and forth, back and forth, back and forth. So the voltage goes back and forth, back and forth. In other words, I have a positive push, then I have, because you can think of the voltage as a push on the charges. And so what I have is a positive push, negative push, positive push, negative push. Sometimes people will refer to the voltage as some sort of an electrical pressure on the charges, and it's not too far off from reality, because if you do have, you have EMF or electromotive force, which is voltage, is always produced by it's generated by the force, electric force or magnetic force, but it's generally generated by the force. And so if you have a force, then you can think of some sort of a push or some sort of a pressure. Pressure and force are different things, but they're related. So what I have here is that the voltage is positive, then voltage is negative, then voltage is positive, then voltage is negative. That means that the current would do something to the effect, current would also vary. So I versus time, if I had that, if the push here is positive, then I would have a positive current. But actually, give me a second, because I have to think about something here. Okay, I thought about what I needed to think about. So if the voltage is positive, then the push is positive, therefore the charges will flow in a positive direction. You can think of it that way. And so what I'm going to have here is, and then if the voltage is negative, then the push is negative, push is in the opposite direction. So we're going to end up with an alternating current where the current flows back and forth, back and forth. I didn't necessarily draw these graphs as corresponding to each other. I just derived sort of in a way intuitively, if you will, the graph for the current from the graph for the voltage. Now the maximum voltage is going to be whatever's in front of sine, meaning this, right? That's just basic algebra, I think. So this is NBA. This would be the maximum. Am I not missing something? I am missing something. In fact, what I'm missing is times omega. There should be omega here, right? There should be omega here. And so this also here, what I should have, let's clean this up. So what I need to have here is that the maximum EMF, is NBA omega. Yeah, that's the maximum. Of course, the minimum here would be the same. It's just that it would have a negative sign. And if I want to figure out the current, then note that the current I is delta V over R. And so from this little expression, I can end up with I as a function of time equals N over R times B times A times omega times the sine of omega t. And so this would be, so the two graphs would be identical, except that the maximum current would have a different value, because the maximum current, I'm going to put the maximum here in the negative side. So the maximum current that you could get is I max would be N over R times B A omega. And I think on your worksheet, this is the equation that I gave you. But the proper equation, or the equation that expresses the totality of what's happening here, is this one. And it's easy to see that all of this is an alternating current, or AC. So alternating current, meaning that the current goes back and forth, back and forth, back and forth, back and forth. All right, so these are the these are the concepts behind the generator. And now I'm going to swing over to the right and we will solve a problem. So the problem I'm going to do is number 1, I think. Let's do that. Simple problem 1. Blue, go to red, let's go to black. So number 1, what we have here is a loop is rotating at 2 radians per second. So I have omega is 2 radians per second. If I wanted to find out what this was as a frequency, that's easy to do. I don't actually need to do it, but this would tell me, I could figure out what f is. And of course, f would tell me the number of times that the loop rotates every second, but I don't need that. And magnetic field is 100 milliteslas, so B equals 100 milliteslas. That would be 0.1 of a Tesla. And I have the radius of the loop, R equals 7 centimeters, so it's 0.07 of a meter. That's going to give me the area because that's just pi r squared. So let's calculate, see what this is. So this is 0.015 meters squared. And what else do I have? I have the resistance, big R of the loop, and that's 10 ohms. And what is the current? And what is the voltage? Okay, so the unknowns are what is the voltage in this setup in this loop, and what is the current setup in this loop, and then the general question whether it's the AC or DC. All right, so well, for a generator, the EMF, electromotive force or voltage, is simply N times A times B times omega. And how many loops do I have? Well, it's a single loop, so N is just 1. Therefore, this becomes 1 times 0.015 times B, which is 0.1, times omega, which is 2. And that's pretty easy to do. What I end up here with is 0.03 divided by 10, so 0.003 volts. And let me pause and make sure that I got this right. Okay, so this is the voltage, but this is the maximum voltage, right? This is just the maximum voltage, really. If I want to find the actual expression for the voltage, what I would have to write is that that would vary with time. And that would be N A B omega times sine of omega t. Or this would be 0.003, where this is the maximum voltage, times the sine of 2 times t. And then I could graph it if I wanted to, right? I could graph this thing, and voltage versus time would be some kind of a sine function here, where the maximum would be just the maximum that I just got, which is 0.003. So this would be the EMF graph. This should curve nicely here, but that's better. Okay, and then of course the current is just, so which one do I want? Let's say the maximum current first. So the maximum current would be the maximum EMF divided by R. And so that in this case would just be 0.003 divided by 10. That gives me 0.0003 amps. That's the maximum current. And if I want the current, the actual current as it varies with time, then what I would have is N over R times A times B times omega times sine omega t. And of course this amounts to 0.0003 times sine of 2t. And that's that. That's all there is for the electrical generators. What I'm going to show you now is a version of an electrical generator that is often shown in physics classes using FET simulation. So here comes the FET simulation. All right, so here's your FET simulation. So here's your FET simulation, and what we have is it's a little different. What we have here is a magnet, and here we have the loop. In fact, we have two loops. We have a coil here that loops twice, and you can see the charges in the coil. So these charges represent positive charges. We will look at conventional current flow. Now what I could do is I could take this loop here and I could rotate the loop near the magnetic field, and I would do the trick. I would get voltage out of it and the bulb would shine. But I could also keep the the loop fixed and keep it stationary, and instead cause the magnet to move. This is not how generators are typically made, but you can do it this way as well. As long as this magnet here rotates, there's going to be a changing flux through the coil, and the changing flux through the coil will imply a voltage setup or EMF setup in the coils, and therefore the charges will flow. So let's open up the water. There goes the water. And as the magnet rotates, the magnetic field changes. The magnetic field through the loop changes, and so the magnetic flux through the loop changes. And that, of course, makes the charges flow. Now note that they will flow like an alternating current. This is an alternating current. So the charges are forced to flow in a clockwise direction and then in a counterclockwise direction because of the way the magnetic field is changing. I get AC. Now, if I increase the speed of this wheel here, I should get a bigger EMF, and therefore these charges should flow a little faster. So I'm going to do is I will do that. Here we go. And now I have more light coming out of it. And that, I think, will, let me see if I can change. Oh, I can increase the number of loops. So if I increase the number of loops, the voltage goes up. And therefore, well, that's all I can do. 3. Oh. Can go to 1 loop, so there's not that much light. 2 loops, more light, and then 3 loops, more light. Okay. I could also increase the area. So if I increase the area of the loop, then I should get bigger voltage from the Faradays law. So if I increase this thing, light. So this is as good as it gets, I think, because I just increased the area to the maximum possible size in this simulation, and then I have maximum possible number of loops. So that will do. Let's stop it. There we go. And of course, here I have water, but I could be using wind for this. I could be using my hands for this if I wanted to. I could also take a burn gasoline in a gasoline engine, and then that gasoline engine will then provide some kind of a rotational motion, and that rotational motion, that the shaft coming out of the engine that burns gasoline could be attached to this magnet, spin the magnet, and spinning magnet gives me current in these loops here. Almost all generators, and maybe even actually all generators, will have the coils spinning within the magnetic field instead of what's shown here in the picture. But both approaches would work. It's more practical to have coils spinning than to have magnets spinning. All right, well, so that's that for the generators.